So it's the electrons that participate in chemical reactions. So we need to know a little bit more about their structure and arrangement to understand how chemical reactions happen. Remember, electrons are very, very tiny subatomic particles that are located in the electron cloud, which is giant surrounding area of the atom around the nucleus. And electrons, although have extremely small mass, they have a -1 charge that is of the same strength as the +1 charge of each individual proton. Atoms are said to be neutral if they have the same negative charge as they do positive charge. That also means that they have the same number of protons as number of electrons. So all the different kinds of atoms that we see on the periodic table of elements, they can exist in a neutral state, which means they have the same balanced positive and negative charges. But that's not always the case. So when a neutral atom loses electrons, remember that it always has the same number of protons. So the amount of positive charge does not change at all and will not change at all for anything that we do in this class, and it won't change for anything that you do in most of your chemistry classes. So protons, and therefore the amount of positive charge in the nucleus, will stay the same. But if that atom, which was neutral to begin with, has lost electrons, it now has less negative charge in comparison to the positive that's in the nucleus. And therefore it has a net positive charge. Therefore, it's a cation. If an atom that was neutral has now gained electrons, it now has extra negative charge, so it's called an anion. So now moving on, we know that atoms can gain or lose electrons. It's a pretty dynamic process, and we'll talk more about that later. I need to mention that the electrons, though in this cloud, they do have a certain arrangement. And it is based on this arrangement of electrons in the electron cloud that we can predict how that atom will behave when it's around other atoms or molecules. And these electrons are organized in what we call orbitals around the nucleus. And it's actually kind of an archaic term that now is not very accurate, because we used to think that electrons circled around the nucleus like planets orbit the sun in a nice, obedient way. So it was convenient to call those areas orbitals. But we now know that they don't do that, but that term has stuck. So when we say orbitals, it just means the area, a certain area. Okay. And with the study of quantum physics, we cannot predict exactly where any electron is going to be at a particular moment, but we know where they are most likely to be in certain situations. So we can't predict it, but we know, like, in general where they reside. You don't need to know the details of this, but I just want to stay accurate in case you're going to be taking crazy quantum mechanics classes in chemistry, so you don't say that I was lying to you by oversimplifying. So the area right around the nucleus, so think of it as a little atmosphere around the nucleus that's really close by, is called the first energy level or the first energy shell. So it's the first area where electrons can be. And this area can fit up to 2 electrons. So if an atom has 1 or 2 electrons, they will be for sure somewhere in that first energy level or energy shell. If an atom has more than 2 electrons, they will no longer fit in there, so they will be arranged in an area that's a little further from the nucleus. And the area that's further from the nucleus is called the second energy level or energy shell. And the second energy level or energy shell is significantly bigger, because you imagine you have a tiny ball, a tiny sphere, and the area around that is going to be small, but the further you go, the exponentially bigger that second area is going to be. And that second area is divided in these other areas that have names and are significant for certain chemistry that you might be doing in your chemistry class. But we're not going to talk about that. So I want, in very basic terms, for you to know that if you imagine a tiny dense nucleus with protons and neutrons inside, the small electron cloud area right next to the nucleus we will call the first energy level or the first energy shell, and it can fit up to 2 electrons. The second energy level or energy shell, so area further away from the nucleus, can fit up to 8 electrons, and the third energy level or energy shell can also fit up to 8 electrons, and so on, just going to continue being 8. You just need to remember the first one only fits 2, but everything after that, for our purposes, fits up to 8 electrons. The energy levels also have letter names, K, L, M, N, and so forth alphabetically, but we're not going to call them by the letters. We will just say first, second, and third, which are also acceptable ways to name them. Depending on what part of that electron cloud, so first energy level, second or third, and so on, the electrons will bounce with the various amount of energy. So the closer they're to the nucleus, the less energy they bounce. The further they get away from the nucleus, they have more energy that they bounce with. And the way to kind of think about it is that nucleus is positively charged, right? Because it has those positively charged protons and neutrons that have no charge, but it has a net positive charge. And electrons are negative, and so they're being pulled in by that nucleus. And the closer they are, that means they don't have as much energy because they're being pulled in tight to bounce further out. Whereas the ones that are further, they don't feel the pull of the nucleus quite as much, so they're free to bounce with a little more energy. But when atoms gain electrons or lose electrons, like when they become ions, the electrons will generally change position. So as this diagram is showing us, the electrons cannot be in between, like have 50% of the energy of a certain level. In order for electrons to move to a higher or bigger energy level, they need to be given energy. They need to take energy from the outside, because it's like they're kind of bouncing, and then the only way to move to the like really bouncy spot is if they get more energy, and they have to get it from somewhere outside of the molecule. So like if the sun shines on them, or they get heated up, or some other kind of energy. We'll talk more about energy later. However, if for whatever reason electrons fall into a smaller energy shell or energy level, they don't need so much energy. They only need a small amount of energy. So the difference in what they had and what they need gets pushed out of the atom and released into the outside. So when electrons move from energy level to energy level, they need the difference in the levels to either be taken in from the outside, or it needs to be pushed out into the outside. Okay, so energy can be gained or energy can be released. Here's another diagram to show you what I'm talking about, in case it makes more sense for you to think about this ball that rolls in steps. And again, do not worry about remembering any of the letter names for these diagrams. It's just what came with the textbook in the previous edition. If we study the periodic table of elements and you notice how they're arranged on that table, you'll know that they're actually not only arranged by size and somewhat by mass, they're also arranged by their electron organization. And I'm not going to teach you more details about that, but chemistry classes will. Even a basic chemistry class will teach you that. Maybe you covered it in high school or in a previous class. You do need to be able to do is, if I provide you with an atom of a particular element, theoretically, like on paper, let's say carbon, you should be able to tell me how many electrons that atom has total if it's neutral. You need to tell me how many are in the first energy shell, how many are in the second energy shell, and how many in the third, or if it has a third. So let me show you an example. Carbon has the atomic number 6. That means it has 6 protons. That's never going to change. That defines a carbon. In its neutral state, it also has 6 electrons because the charges need to be equal. If the first 2 electrons must settle in the lowest energy shell, that means the first 2 of the 6 go in the first shell. How many are left over to go into the second shell? 4 are left over to go into the second shell. So, and the reason why we need to understand this is because it is the electrons on the very outside energy shell, whatever that is. For carbon, as we just talked about, it is the second energy shell that has 4 electrons. So it's the electrons that are on the outside that do all the chemistry that we're interested in. Therefore, those electrons that are in the outermost energy shell of that atom, they have their own name and they're called valence electrons. And the outermost shell, or the outermost energy level for a particular atom, is going to be called the valence shell, or the valence electron shell. For example, the second energy shell in carbon is the valence energy shell. Whereas for hydrogen, which only has 1 electron, the first energy shell is the valence and energy shell. There is a tendency for electrons to want to do whatever they can to fill up their valence energy shell. So atoms are most stable when their outermost energy level has a total of 8 electrons. And practice for just a couple of minutes figuring out the number of valence electrons for each particular atom in this slide. And go ahead and do that by writing the symbol for the atom that we're talking about, and that symbol can signify the nucleus, and then draw a circle for the first energy shell, determine how many electrons can go in there, then if necessary draw the second energy shell, determine how many electrons go in there, and then if necessary the third. And then underneath write number of valence electrons equals, so that you're sure that you understand what that is before we move on. Notice from your practice problems that the atoms that are on the rightmost column of the periodic table, they have 8 electrons in their valence energy shell. Because atoms are most stable when they have 8 electrons in their valence shell and no more and no less, these atoms don't need to interact, and they really can't interact much with other atoms because they have everything they need. They don't need anyone else. The octet rule, octo is for 8, octet rule says that atoms are most stable when their outermost energy shell is filled, which means that they have 8 electrons. I should point out right here that the exception is hydrogen and helium, the 2 smallest atoms. They only have the first energy shell, and therefore their valence energy shell is filled when 2 electrons are present, and then they are satisfied. So it's in general, it's called octet 8 rule, but for helium and hydrogen, same principle, but they don't need 8, they only need 2. And it's this need to gain or lose or share electrons in some way to get that valence electron shell filled that motivates these atoms to interact with other atoms. Molecules are groups of atoms that are held together in somewhat stable associations. Compounds are specific subtype of molecules that are made up of more than one element. Okay? And atoms are held together in these molecules, in these stable associations, by chemical bonds. We'll talk about ionic bonds. So ionic bonds are a type of bond that happens when oppositely charged ions attract one another. Okay. So in order to have ionic bonds, we first need to have ions. And let's look how an ion can form. Sodium as an element, as a pure element, if you just have a bunch of sodium atoms from the periodic table and you put them together, it is a soft metal that can be cut pretty easily with a regular knife. And that substance is quite explosive. If you were to accidentally get some water on that, you would have an explosion. So it's a volatile substance. Chlorine in its pure form, if you just have chlorine atoms that are neutral stuck in a container, it's a yellowish greenish gas that is extremely toxic. And if you were to inhale that, you would have brain damage. So if we take pure sodium, elemental pure neutral sodium, and we take this pure chlorine and we put them in the same container, they're going to react and create a completely different substance that you're very familiar, which is called sodium chloride, and it is table salt that we use for flavoring our foods. Why does that happen? Notice here that sodium has 1 valence electron. Oh, bummer. The stable way is to have its shell filled, and because it has 3 shells, it needs 8 electrons. And in order to get there, this atom could gain 7 electrons, or it can just get rid of 1. And either way, it will have an octet, or a filled valence shell. Well, gaining 7 electrons is basically impossible for this atom. It's just too much, and that nucleus is not going to be able to hold on to all those extra electrons. So sodium generally tends to lose an electron. But you can't just like throw it out there into the universe. Something has to pull it away from you, just a little bit at least, so you can get rid of it. Now, pause, and let's look, don't pause the video, just pause that line of thought, and let's look at chlorine, okay? Chlorine has 7 valence electrons. Oh, so close. If it only could gain 1 more, it would have a full valence electron shell. So when sodium and chlorine happen to be physically close to one another, it's a very convenient situation for both atoms. Sodium can get rid of 1 electron, and chlorine can grab that electron. Beneficial for both of them, so it occurs spontaneously and very quickly. And once that electron moves from sodium to chlorine, chlorine is really excited about it, and now it becomes extremely stable because it has its valence shell filled, and it holds on to it for a very long time. Like, it basically permanently keeps it unless there's a much, much, much stronger force that would take it away. So now chlorine has one extra electron, and that makes it an anion. Remember, negatively charged atoms are the ones who have gained electrons. Number of protons in the nucleus stays the same, 17 for chlorine, but now instead of having 17 equal electrons, it has 18. So 18 negative charges, 17 positive charges. It has a net charge of -1. So it's a negative atom that we call an anion. And sodium, again, always keeps the same number of protons, positive charges, but it has now lost an electron. So it has a net positive charge. And therefore, this sodium in our particular situation has become a cation. So this is how ions can form. And now that you know how ions can happen, we're going back to talk about the next step, which is ionic bonds. And ionic bond simply means that if out there happens to be a negatively charged ion, and in the same area there happens to be a positively charged ion, they, like magnets, will just stick to each other because positive and negative attract to one another. So ionic bonds are an attraction between oppositely charged ions. In the case of table salt, it forms these very regular crystalline patterns, negative, positive, and so on, because that is the most stable way for the charges to interact. The actual formation of ions, that's not an ionic bond, okay? I hope that that's clear because I often find that it is confusing to students. If you were to take this table salt and put it in water, even cold water, stir it a little bit, then the sodium ions and the chloride ions, they're now called chloride, it's just a weird naming thing. Chloride ions, they'll separate and they'll float around separately, but they will keep the extra electron or be rid of the extra electron. They will float around the water with their charged versions. Atoms can gain their octet or fill up their valence electron shell by gaining electrons or losing electrons, just as we saw. But they can also gain that stable state by sharing their valence electrons. And this sharing is called covalent bonds. So think of co is like together. Like when you cohabitate, you're living with someone else. So covalent bonds are bonds when there's sharing of valence electrons. This works when at least one pair, which means 2 electrons, are shared between 2 atoms. And covalent bonds can be of various strength depending on how many pairs of atoms are shared. So we can have single covalent bond when 2 electrons or 1 pair is shared. A double covalent bond means 4 electrons are shared, and a triple covalent bond means when 6 electrons are shared. Let's look at the simplest example, hydrogen atom. Hydrogen only has 1 electron in its valence shell, and in order to be stable, it really would like 2 electrons. When there's 1 hydrogen atom, there's usually another hydrogen atom in the vicinity. And since they both need 1 more electron, it works for them to share the single valence electron that they have in order to have 2. Their electron clouds will actually attract to one another and kind of overlap. And this overlapping means that each hydrogen is contributing their 1 valence electron to be shared between the 2 nuclei of the 2 hydrogens. This molecule is then called H2, meaning that there are 2 hydrogens, and it's written H, which is the symbol for hydrogen, and underscript subscript 2, meaning that there are 2 of them. Okay? 2 hydrogens, they're stuck together in pairs. In fact, a bunch of the air you're breathing right now is made up of hydrogen gas, and when we say hydrogen gas, we mean that it's these hydrogen atoms in pair, which is molecular hydrogen, because it's now a molecule. This slide shows a couple of more examples. So oxygen actually needs 2 more electrons in order to have its outermost shell filled. And in order to do that, 2 oxygens can come together and share 2 pairs of electrons. So go ahead and count how many electrons each oxygen has in their valence electron shell. They each have 8. Because 4 electrons are shared, this molecule has a double covalent bond. And in fact, yes, the oxygen that we breathe that's in the air right now is all floating around in pairs as molecular oxygen, which means the pair of oxygens, because they're much, much more stable than a single oxygen atom. And the last example here is nitrogen, also in our air. In fact, it's the most prevalent gas in the air. And nitrogen is also 2 nitrogen atoms bonded together with 3 pairs of shared electrons, making it a triple covalent bond and the strongest covalent bond that there is. In fact, it's so strong that although nitrogen is the most prevalent gas in air, it is generally the limiting factor for how well plants can grow, because they need a lot of nitrogen and usually there's not enough. This is because plants cannot break the triple bond of nitrogen in the air, and the 2 nitrogens together are completely useless because they're so happy in their pairing that they are never going to do anything to interact with the plant's mechanisms. So there's only a few critters out there, mostly bacteria, that are able to break up molecular nitrogen, break that triple bond so that individual nitrogen atoms can then be used to incorporate into other molecules in other ways.